Good afternoon. I am Sarbajit Pal, head of the Computer and Informatics Group, working in VECC. This is a part of the lecture series for the celebration of Azadi ka Amrit Mahotsav at VECC. I would like to deliver my presentation on various aspects of control system for the automation of cyclotron. The title is Control Aspects of Cyclotron. Cyclotron, it is a particle accelerator. Accelerators speed up charges like proton, heavier ions, bunch them into a beam. The beam hits the target. Scientists gather information to understand different atomic properties. I shall begin with the application of particle accelerators. Accelerators are being used as radiation sources for various purposes in basic research application, research in solid-state physics and material science, analysis of material using particle beams, then medical application like radioisotope production for medical imaging in SPECT and SPECT, radiography. Then it has industrial application also in food preservation, product sterilization, sewage treatment. Also it has application in energy production. Cyclotrons are widely used to accelerate charged particles in nuclear physics experiments. It is used for nuclear transmutation, that is change of nuclear structure. For radiation therapy in the treatment of cancer, different cyclotrons are used. Radioisotope like gallium-67, 68 has been successfully produced by VECC's medical cyclotron facility at Kolkata. This is the content of my talk. With a brief introduction of the working principle of cyclotrons, I shall discuss various features of distributed control system. What are the different subsystems of cyclotron? What the subsystems need to deliver? What control system we have and for different subsystem control. It will be followed by open source SCADA implementation at VECC, some utilities applications developed at VECC, and this will be followed by future plan like development of SCADA embedded controller for subsystem control, attempt towards complete automation starting from automated internal beam tuning, extraction and transportation to the target chamber, and concluding remark as what we mean by a good control system. So lean up. When the shape of the accelerating chamber or the path of the beam is linear, we call it is a LINAC or linear accelerator. Here ions are impelled to gain energies in a straight line. Here we see within a cylindrical evacuated chamber, particles are getting accelerated. RF energies are supplied by providing high voltage. The particles are injected here. It's getting accelerated in the gap because alternate tube is having the alternate polarity. So in cyclotron, proton and ion beams are energized while traveling through a circular path within this evacuated chamber. Here there is a large electromagnets on the top and on the bottom, and a charged particle moving in the normal to the magnetic field. It experiences magnetic Lorentz force, and due to this, particle moves in a circular path. In the left we see the two cyclotrons at VECC. One is room temperature cyclotron and one is superconducting. The room temperature cyclotron, it is operational since 1977. It is K130. The K value specify the maximum energy of proton that can reach for its bending strength. For superconducting cyclotron, K value is 500. The bending strength increases with the magnitude of the magnetic field. The average magnetic field in room temperature cyclotron is around 17 kilogauss, and superconducting cyclotron it is around 49 kilogauss. So this condition of isochronism, it is very important for particle acceleration. The moving particle, it rotates in a uniform magnetic field. The rate of rotation of a specific charged particle, we call it cyclotron frequency. Here two D-shaped cavity, one is positively charged and another is negatively charged by alternating RF field. One D attracts and other D repels the charged particle, and particle gets accelerated at each gap while crossing. Here we can see the time period of the RF is the same as time required for a particle to travel one turn. So in this accelerating gap, particles see the same RF phase. So using the beam phase measurement system, we can get the beam phase information, and with the help of beam current and phase information, which is required to get optimized beam. By optimize, I mean very less loss of internal beam in the accelerating range inside the cyclotron. Now it shows various components or subsystem of a cyclotron, like ECR ion source, vacuum system, RF system, magnet power supply, internal and external diagnostic system, field mapping, low conductivity water cooling system, trim coil cooling system. So for each system we have a distributed control system, we call it DCS, and all the DCS sit on a control LAN. Here heavy ions from ECR is actually injected at higher potential A spiral inflector is used to place the injected ion in the median plane of the cyclotron. In the high vacuum is desirable in the accelerating chamber. The requirement of the high vacuum is around 10 to the power minus 6 millibar for room temperature cyclotron and around 10 to the power minus 8 millibar for superconducting cyclotron. So RF is an important subsystem. It has a operating frequency range. RF power is fed to D through the D stem. Then it has a main electromagnet. It is a solenoid coil which is fed by the magnet power supply. The stability requirement of the power supply is very stringent. A local control loop is used to attain the stability. At present, embedded system is used for achieving the required stability. There are also several trim coils and related power supply. These trim coils are for magnetic field tuning, correcting the harmonic variation in the magnetic field at different radii. In the beam extraction system also, it is comprises of electrostatic deflector and magnetic channels. So here there is a diagnostic system. This is to measure the beam properties at various places of the cyclotron. Accurate measurement of the magnetic field is also important. So from the field map system we can calculate the first, second, third and higher harmonic content in the magnetic field. This diagnostic facility helps to correct the magnetic field. Each of these system is controlled by distributed control system, and with the help of a SCADA, this is supervisory control and data acquisition system, we view the various parameters of different system at the central console. Now, what is the control system requirement? This is the basic control system requirement is to read, set or monitor the process variable, that is various process parameters. Some parameters need to be set and some are to be monitored. Then data logging, that storing of some important process variables and events. The good control system needs to set and get PVs through low-level access. So there will be a facility for powerful and easy development tools, and it can have a facility of standalone operation. OPI is the operator interface. It should have very rich operator interface. There should be meter, command button, slide bar, soft knob, chart and trend, that is real-time charting facility. Obviously, the system should have a very quick response and it should record key operation for use in automation or for audit. So here it is modes of control. Computer regulates the operation of the system or the process. So there is different type of control: logic control, on-off control, linear control, open or closed loop control. Here we see the example of a direct digital control and supervisory control. This is DDC, we can call it supervisory control or SC. In DDC, the flow rate directly goes to the computer, and the valve setting, the information that comes directly from the computer. Whereas on the other hand, the supervisory control mode, there is a local controller which controls the flow rate. The actual flow rate feedbacks goes to flow controller. Only the flow rate set point, that value comes from the computer. This FC, this flow controller, is a local PID controller. So this is a typical feedback control example. Generally PID controller is used, that is a proportional integral derivative control. In proportional control, generally correcting action is proportional to the deviation, and in the derivative it is proportional to the rate of change of deviation. In integral, the rate of change of correcting action is proportional to the deviation. So there are several methods for tuning PID loops. Here we see the various components of control system. Here is a process parameter. Some of them are controlling parameter and some are monitoring parameters. There are different interface, so different ports, protocol and data communication it supports with the computer or the controller. So list of parameters are given here. So here is the measuring parameter. So a transmitter is a process control. It is a device that converts signal produced by a sensor to a standard instrumentation signal. So PV, a process variable, which is to be measured and controlled. Now we see the various control hardware. One is pneumatic control. This is the control hardware type. They are pneumatic control, analog control and digital control. The signal transmitted pneumatically are slow and susceptible to interference. Here the computation devices are mechanical, so it wears out quite quickly. In the analog control, analog signals are susceptible to noise. Signal degrades over a long transmission line. Computation using the analog devices is still limited. Whereas in digital control, it is far less sensitive to noise. The computational devices are digital computer, microcontroller, digital signal processing chip. So here we see elements of control software and hardware. These are the controlling or monitoring parameters. These are the actuators, different. These are different types of controller and their software. In the controller we see some of them are controllers and some of them are interfaces. They are being used for cyclotron control of VECCs. There is an embedded controller, in-house developed, field point module, PLCs, and some intelligent measuring devices. For GUI development, we have used SCADA tools like Epix, LabVIEW, VV, and some of them are proprietary software. This is the typical control loop. So a controller, from the process, it takes process value, we call it PV, and on the basis of the set point, the control output is generated to control a process. Now we'll see the elements of local controller. The local controller of a distributed control system or a SCADA, that is supervisory control and data acquisition system. We use single board computer, PLCs, embedded systems. So more generally, PLCs are used. The component of PLCs are power supply. It has 4 sections like power supply section, input output section, processor, and programming section. The difference of PLC and embedded system or single board computer, it is PLC has, in the PLC controller unit, we can have several PID loops can run simultaneously. And another important feature is the sequencer. The PLC sequencer is a consists of a master counter that has a range of preset counts. So as it runs, when the preset count reached to a particular value, it can be used for control outputs. So each steps in the count sequence, it set certain output or group of outputs. So as a local controller, we have embedded systems also. Various embedded systems are available. Standalone real-time embedded system. The C or C++ is used for program development for a embedded controller. Can use OS like Windows C, Linux, and Android. Presently, very popular embedded system is a Raspberry Pi. It has an embedded Linux. It's run on ARM processor. This is a typical architecture of a distributed control system. There is some difference between distributed control system and SCADA. In DCS, it is a process control system, DCS, that use network to connect sensor, controller, operator terminals, and actuators. And the core of the DCS is PLCs. So what is the advantage? The advantage of DCS that it can control more than one system at the same time, because it has a support of automated local controller, and all the individual local controllers are connected to the central controller. They are connected via very high speed data link. Now the SCADA, the supervisory control system, it may be called as a human and machine interface. The features are, it gives the live monitoring of system parameters by real-time data access. It gives graphical interface and web interface, meaningful alarm description. It has industrial grade durability. There are other advantages. We can increase the reliability, reduce the cost, improve utilization. The difference of SCADA and DCS is basically process oriented, and SCADA is data acquisition oriented, because DCS does the continuous control, and SCADA control is generally it is event driven. DCS can handle single or multiple process, but SCADA is preferred to have a multiple process. Mainly they are spread over a vast location. So DCS consists of one local controllers, one or more local controller, and they implemented advanced process control techniques. But in SCADA, system cannot carry out advanced process control technique. The advanced process control is generally handled by the local controller, very local controller PLC. SCADA software generally monitors the overall performance of the loop. So we see the use of EPICS tools, utilities and application for development of supervisory control and data acquisition system of VECC. So development of various tools, utilities and application I'll discuss later. Now I will give a brief overview of cyclotron subsystems, the control features of various cyclotron subsystems. This is control system architecture. It comprises of control network and laboratory network. The SAN has independent network. It connects the devices for sharing storages. All the DCS are connected using the control LAN. As a DCS, we have in-house made embedded system, standard measurement devices with network connectivity. We have PLCs. We have controller with multi-drop serial connectivity, field point modules, etc. Now the core of the control system is the backbone of the control system is our control network. It is isolated from VECC office LAN. It is based on two-tier star topology. It provides gigabit backbone and end-to-end connectivity. Its nodes level speed is 100 Mbps. It can tolerate single switch or single link failure. It has a network management software, helps to monitor the performance, and it provides the report on uptime of the network. Here we see our modernized control console. We can see mimic display, LED panels, control switches. Some of the LED panel meters are partially replaced by the computer monitors, and fine-tuning knob for the power supply. We call it soft knob. Another important subsystem, it is a diagnostic system. It is magnetic field mapping system. The system scheme is shown here. It shows the connectivity among the different diagnostics and control equipment. The main magnet power supply and trim coils power supply that energize the main magnet. The top and bottom poles are shown here. The pink structure is the jig, and the vertical stem of the jig rotates 360 degree, and the horizontal arm scans the complete circular magnet. The complete scanning is done several times to obtain this magnet field map at various power supply settings. This slide shows the different instruments used, like Tesla meter, digital integrator, linear encoder, absolute encoder, and their stringent measurement range and accuracy is given here. The total system setup is shown here. It shows the search coil movement on the pole tip, and this is the rack where all instrument has been kept. The salient features are this system can perform 100K data point logging within an hour. Other stringent accuracy and resolution features are shown. Very precise instruments are used. The main thing is that here PC based client server architecture was used, and the software is developed using C and LabVIEW. So this slide shows the benefit of measurement. From the measurement we can find there is a deviation from threefold symmetry. So this deviation in the average field as well as in the harmonics content we can see, and from this finding this has been corrected by adding iron sheave, and better average field and less harmonic contents was obtained. So now you see the OPI of cryogenic delivery system. In the cryogenic process, liquid helium and liquid nitrogen required to circulate. This is required for cooling the main magnet and cryo panel. The cryo system has helium refrigeration and gas management system, liquid helium delivery system, and liquid nitrogen delivery system. The automation of this system is managed by PLC. The operator interface, data archiving, alarm system is implemented using EPICS utilities. So for this control, there are several sophisticated sensors like liquid nitrogen, helium level sensor are developed. Also, cryogenic temperature sensors are also developed. Now it shows the magnet power supplies. In superconducting cyclotron, we have two magnet power supply, 18 trim coil power supplies. The MMI is used, window based, developed in VECC. All the power supplies are equipped with intelligent controller and serial transceiver, and can be operated and monitored remotely over a serial link. So this is the control architecture for power supply control system. The serial links are used for accessing the power supply control to the supervisory control monitor. The GUI of main magnet power supply and trim coil power supply is shown here. It is another main system, that is ECR system. The ECR systems generally it consists of several high current magnet power supply, microwave generator, and various beamline equipment like gate valve, Faraday cup, slit, and collimators. So the main control system is based on proprietary field point modules, and the control application is written in LabVIEW. So entire setting of parameters and control and monitor from remote location, and it is done from cyclotron control room. Another main system is vacuum system. The process flow diagram of both the cyclotrons or vacuum systems of both the cyclotrons are shown here. The auto startup of the vacuum system requires sequencing of operation of various pumps, valves, and interlocks. The pumps are rotary, diffusion, and root pumps. and there are gate valves and interlocks. The control system of room temperature vacuum system has been upgraded to PLC based automated system from the relay based manual system. And in the superconducting cyclotron, here actually distributed PLC system is installed for this controlling this superconducting cyclotron vacuum system. The requirements are reliable local and remote operation for vacuum component and instrumentation. So vacuum control system has been implemented using EPIC's distributed real-time software tools. There is a LCW plant monitoring system. This system, it is done using proprietary data acquisition module which supports Modbus TCP protocol connected over the control LAN. Similarly, the trim coil cooling water temperature control system, this is monitoring several process parameters: temperature, pressure, flow, conductivity levels. The system controls the temperature of the coil cooling water, conductivity of the water, and the surge tank level. The system provides interlock to the trim coil power supplies. Here, proprietary SCADA-based GUI communicates with proprietary redundant controllers in Modbus RTU protocol. So now we come to beam diagnostic system. So here the list of beam diagnostic components like main current probe, viewer probe, slit, magnetic channel, inflector, Faraday curve beam viewers. This is the view of internal 3-finger probe and beam view probe. It is shown here. So a very low current measurement instrument is developed for this purpose. This instrument has 2 auto-selectable channels that measures current from 1 nanoampere. This instrument is used for measurement beam current in Faraday curve, slit, and internal current probe of the cyclotron. This shows the scheme of the view probe of the OPI. The OPI is developed using Visual Basic components. This is the OPI for internal current probe, movement control. This shows the component in beam extraction systems. They are deflector and magnetic channels. Their positions and beam current for falling of deflector and the magnetic channels are measured. The position setting are also done using the same OPI. So we see that our system, it is a heterogeneous control system for subsystem control. So we adopted PLCs, proprietary controller, lab design embedded system. These things are used for local controller. These controllers are connected to engineering station dedicated to a specific system, and engineering stations are connected to the control LAN. So a supervisory control system provides operator to have a integrated view of the all subsystems at the operator control console. So now I'll describe about the features of supervisory control system. We used EPICS. It is a open source software tools. It gives several utilities, libraries and applications. So one of the main important feature it is that it has been developed collaboratively. So this has been used worldwide. And it provides libraries for development of the distributed system, mainly soft real-time control system. The EPICS also provide tools for development of distributed control system. Here are several features of distributed control system supported by EPICS is given, like remote control and monitoring of process variable. It gives closed loop control, alarm detection, reporting, logging, automatic sequencing, modeling, simulation, data acquisition and data analysis. So EPIC has all the main features of SCADA as well as DCS. So our monitoring and control philosophy is like that. We have adopted single layer architecture for control LAN. Host computers for each subsystem is connected to the control LAN. Here one computer is dedicated to the one control subsystem. For ease of control, console is shared at the time of beam tuning. There are dedicated several central monitoring of vital parameters, data storage and historical charting. These dedicated servers are there. Now, what is the advantage? What is the advantage of EPICS I have told, but how the EPICS does all the work. EPICS uses client server and publisher subscriber technique to communicate between server and the client. Here server or hosts, they are called the IOCs. This is the input output controller. They execute real world input output operation. and controlling the local task. It also publishes information to the client. So using a channel access network protocol. The properties of the protocols are it provides high bandwidths and soft real-time performance. So soft real-time means it can tolerate some delay in the non-critical system. Here the main function is accessing process variables or process parameters. So each process variables or process parameters, they are assigned to a channels. Channels are, it is a connection, it's a virtual connection between a server and the client. And this, the monitor, it is another process which is created on a channel and it gets asynchronous notification of the change in a process variable. There is another repeater process. It allows several clients in a same computer to share the same port. In the most of the network stack implementation, this facility doesn't support it. So if you see the overall operation, the goal of the channel access protocol is to provide remote access to PV by IOC server. So IOC has done this host. They give several beacon signals for knowing their PV availability, and this is periodically sent. So all they used this beacon signal to restore, to start a connection or to restore a lost connection. So client does the host discovery, it establishes virtual connections. This establishing a connection is called registration. When a client is registered, it gets event notification. So all our GUI of different subsystems, we have used components. These VV components are channel access compliance. Now one of the major feature is that implementation of the control database. So Epic's tools are used for interfacing open source database. This has been developed in-house. It has built-in web server for distributed viewing. The online viewing in text and in the trend plot is possible by using a browser. It provides historic data analysis facility, graphical comparison of archived data. Here we see the screenshot of online textual and trend plot in the browser. This is the GUI. It is also termed as operator interface or OPI. So Epix provides library function that can be integrated to the graphical control components available in Visual Basic IDE. So channel access is embedded in Visual Basic components like text, image, command button. The advantage is using drag drop type, easy graphical type of code facility. Very easily the GUI of the distributed control system can be developed. In figure, it shows the GUI of the interfacing slit controller used in beam diagnostic application developed in Visual Basic. So now comes the hardware part. So we have already developed Epic's SCADA software. Now VECC has also developed in-house embedded controller system. The embedded system has a communication controller and various function modules. And these modules are connected over a backplane. The different modules are digital I/O, analog I/O, precise current measurement modules, stepper motor, DC motor controller, driver, readout for various optical encoders. Here some modules are intelligent and some modules they are local group control. Running is possible. So we made this communication controller an intelligent module as a Epic's embedded controller. Now the diagnostic controller. The earlier system, it was a TCP client server or multiple serial connectivity was there, but we have used embedded Epic's tools to be used as a server. So we have chosen very small footprint Epic server. It was implemented with channel access protocol. The tiny Epic's was embedded in the communication controller. The communication controller pluggable module based on instrument to cater general requirements of beam diagnostic system. We used ARM based or FPGA or PSOC based communication controller as a embedded Epic's controller. So how to choose a controller? The controller should have industrial standard embedded microprocessor architecture. Controller should have low power consumption, small footprint, low cost. If it is FPGA based, soft IP cores for peripheral integration should be available, and controller should have license from multiple manufacturer. This will mitigate its obsolescence, and it should have a compatibility with Linux OS, GNU-C compiler support. Now this shows several Epic's enabled controller what we used in our system. In-house designed Epic's controller using FPGA. We have seen several types of process runs well in the controller, and some high-speed processing runs very efficiently in FPGA. So this was done. This is a controller based system, what you see in the embedded controller, but we have done using FPGA. FPGA communicates with the controller by using a glue logic. The logic means This logic makes connection from one to another device. It glues basically two different ICs. Suppose we have a FPGA that has a specialized function, for example, very high speed I/O processing. When we want to interface FPGA to another I/O protocol or a standard bus like I2C or RS-232, we write a small code in the FPGA portion and glue this FPGA and CPU together. So having this idea, we have developed such board where this is a FPGA board and this is a piggyback board comprises of microcontroller. So this is the ARM-based embedded EPICS IOC module developed in-house. It has been used commercially available off-the-shelf SBC of industrial grade. It has a very small form factor. It has an inbuilt Ethernet interface, preemptive Linux kernel. The one of the most advantageous thing is it has a dual redundant power supply. It allows access of predefined users. The operating system and application software are stored in a removable 4G memory. The image of the memory module is stored in the centralized server as a backup. This IOC has been tested more than 72 hours continuous runs without failure. This shows the salient features of the Diagnostics controller. This embedded diagnostic controller have a EPICS embedded communication controller. The targeted diagnostic devices are main probe, fever probe, then XY slits, beam viewer, Faraday cup, and different valves and interlocks. This operator GUI using VB with channel access components has been developed. Now, beam phase measurement system. We have in-house developed beam current measurement system module. So this shows the internal interceptive type of beam phase measurement system. We have also planned for develop non-interceptive type of beam phase measurement system to obtain beam phase profile. The beam phase profile shows here. We can find the acceptable phase position of the beam at different radii, that is at injection, accelerating and extraction zone. So use this facility with this diagnostics facility. We may now plan to develop a simulation program. The outcome of this simulation program is a virtual development of a virtual cyclotron. This should meet the criteria that it should be reliable in producing the reasonable physical result. It has to be fast enough, and the computation should be about the same order as it is obtained from real-time system. To make the model interactive, real-time response is essential. So it should be able to calculate physics value and should generate diagnostic signals. This is necessary for development of a control program. This will in turn simulate and provide us set of machine parameters for tuning the new ions and help beam physicist for faster beam extraction. So, as a concluding remark, I must say our goal is to develop a control system which is very reliable. Reliability means the trustworthy and a satisfactory performance it gives in a specified environment. Perform consistently without error or fault. So it gives accuracy over time across different platform and devices. So we need to have a better quality of components. We need to have incorporate redundancy. Need to use component from different manufacturers. And also system should be available. The availability is the probability that the system is operational when it is needed. This indicates the system's uptime. It is the ratio of runtime over the planned operational time. Another feature of a robust system should be its maintainability. The system can be easily repaired or serviced, so operation can be restored in the minimum time. So it will depend on the availability of the design drawing, documentation for the troubleshooting, availability of skillful personnel, use of standard part and equipment. The equipment should be off the shelf, readily available, and if we have a planned maintenance program, then maintainability can be improved. In other words, good maintainability improves the availability. And there will be features like upgradability, the modular design, both software and hardware, and use of open source software, open source protocol. All this together ensures the long life of the control system. That is the goal to achieve for a control system. So I acknowledge the contributions of all the members associated with the development and implementation, and also all the members of EPICS community. Thank you, and that is all about it. I would like to thank the audience for your interest and attention. So I conclude my presentation. Thank you.